So here's our vector equation of the line. R0 is the position vector of the point that gets you on the line, V is the direction vector of the line, and multiples of that direction vector move you up and down the line. So here's the Wolfram demonstration that I wanted to show you. So here you can see X, Y, and Z axis, and then the line is right here in green. And the point to get on the line is 1, 2, 1. The direction vector is 1, negative 1, 0. And then this is the final point that's on the line. So here's the slider for t. As you vary that parameter t, you can see this point right here go up and down the line. And that's what I wanted to show you in class on Friday, was you're going to need a point to get on the line, and then multiples of that direction vector slide you up and down the line. So it's just like slope in 2 dimensions. So what's up next? Well, we found parametric equations for that line. Our direction vector was P0P, and then we took multiples of that to slide up and down the line. Where does it intersect xz plane? Xz plane was y equals 0, so we set y equals 0, found a time, and then plugged that in for x and z, got our point here. Next question, or next part of the question, we're going to let L2 be the line with parametric equations 2t, 1, and 3 minus 2t. We want to know, is line 2 parallel to line L? Well, two vectors or two lines are going to be parallel in 2 dimensions if they have the same slope. In 3 dimensions if they have the same direction vector or a multiple. So our first direction vector, we'll call that V1. So that was right here, 1, negative 4, negative 3. And then the direction vector for this line L2, well, we're given the parametric equations here. If we write this in vector form, this is going to be R of t equals our point to get on the line, 0, 1, 3. And then we're going to add multiples of, so this will be t times 2, t times 0, t times negative 2. So 2, 0, negative 2. So here's our second direction vector, 2, 0, and negative 2. And these vectors are not parallel because they're not multiples of each other. So vector 1 is not parallel to vector 2. What we would need is, we'd need that vector 1 is some constant multiple k times v2. So like 2 times v2 or negative 1 times v2. So no, these guys are not parallel. Direction vectors that have to be parallel. Here's a line L3. It's 0, 1, 3 plus t times negative 2, 8, 6. Is L3 parallel to our original vector? Well, our direction vector, V3, these are vectors with arrows on them, is going to be right here. So negative 2, 8, 6. And now we want to compare that to 1, negative 4, 3. Well, to get from 1 to negative 2, you'd have to multiply by negative 2. And if you multiply by negative 2 here, and let's see, oh wait, was that a negative 3? It was indeed a negative 3. Minus 3. If you multiply by negative 2 here and here, you'll get your 8 and your 6. So notice that this is negative 2 times the vector 1, negative 4, 3, or negative 2 times the direction vector v1. So yes, those are indeed parallel. So parallel lines, parallel direction vectors. The lines L and L2 up here, we said that they're not parallel. Are they skew? So skew means that they're not parallel and they don't intersect. So if two lines intersect, then their x, y, and z values have to be the same at some point in time. So here's the parametric equations for line L. Here's the parametric equations for line L2. And we want to know if they hit each other. Well, it doesn't have to happen at the same time, so let's use a different variable here for our second line. Instead of t, let's use s. And so we want to know, are there times s and t where x, y, and z coordinates are equal? So, well, here we've got a constant. That's the easiest y coordinate. Let's set these guys equal and find t. So set the y coordinates equal. -1 minus 4t has got to be equal to 1. Bring that -1 over as a positive. So we would get -4t is equal to 2. In which case, divide both sides by -4. T is -1/2. So if t is -1/2, we can plug that in here, and then we've got an equation there. Plug it in here, we got an equation there. So if t is -1/2, plug that in the first equation. That gives us x coordinate of 2 minus 1/2 has to equal 2s. So this is 4 halves minus 1/2, 3 halves. So 3 halves equals 2s, and divide both sides by 2, so then your s is going to equal 3/4. So now we've got values for s and t. So if these two times are going to work, they have to work in the z coordinates here. So let's take t is -1/2 and s is 3/4 and plug them in and see if the z coordinates are equal. So the z coordinate here, 3 minus 3t, so 3 minus 3 times -1/2. We're asking question, is that equal to 3 minus 2s? So this would be 3 minus 2 times 3/4. So let's see here. Double negative will make a positive. 3 plus 3 halves, so 9 halves plus 3 halves is 12 halves, or 6. Did I do that right? 3 plus 3 halves. No, I'm sorry. That'd be 9/3. In halves, it would be 8. 8 halves plus 3 halves, 11 halves. So we're checking is 11 halves. Is that equal to... this would be 2 goes into 4, 2 times 3 minus 3 halves. So that's 8 halves minus 3 halves, 5 halves. And no, those two are not equal. So they are not parallel. And then what this shows is that they don't intersect. So they are indeed skew. And just to kind of get the idea of what skew means visually here, probably should have showed you this first. Think of a box. And your picture of skew lines would be, I'll do one in red. Whoops, keep that one in blue. So this line down here, and for example, this line up here. Those two lines are skew. They are not parallel to each other, and they do not intersect. So if I drop that one down, they'd be perpendicular. But since there's some height between them, they are not perpendicular, not parallel, don't intersect. So these are skew lines. Okay, so having a Cadley quiz for you, try the first quiz question.